Right now, as you watch this, 17 nations and dozens of private companies are in a sprint, a headlong rush to plant their flags on the dust of other worlds. Your screen is flooded with it. The headlines scream about lunar bases, Martian cities, orbital factories taking shape in the void. Rockets tear through the sky somewhere on the planet almost every other day. Billionaires duel with stainless steel giants, nations maneuver in the high frontier, and astronauts from multiple countries are living right now in that thin shell of metal and light sailing silently over your head. It feels electric, undeniable. This modern space race appears more alive, more furious than any moment since Apollo. The momentum seems absolute. But I need you to look past the spectacle, past the thunder of engines and the glow of headline triumphs. Because beneath it all, pulsing quietly beneath every launch and every declaration of permanence, lies a crisis, a single devastating point of failure that no mission controller, no CEO and no president wants to discuss. Every single spacecraft, every astronaut, every piece of equipment we have operating beyond Earth at this very second is hanging by a thread that stretches back to one planet. Sever that thread, cut that supply chain from Earth for just 90 days, and everything we've built out there dies. Everything. We have spent 70 years and uncountable fortunes proving, beyond doubt, that we can reach space. We have spent exactly 0 years proving we can stay there without Earth. This isn't the story of the race to the moon or to Mars. This is the story of the race. Nobody is actually winning. If you want to understand why the glittering future of space exploration faces a problem that more rockets and more money cannot solve, you're in the right place. Let's get into it. Where are you watching from? Let me know in the comments below. I read every single one. And if you're ready to see the race for what it really is, hit that like button and subscribe to this channel. This is where we see the bigger picture. Open any newsfeed, any stream, any article covering space, and you'll be bombarded by statistics that scream a new golden age. Last year alone, we launched rockets from Earth more than 250 times. Think about that number. A controlled explosion lifting thousands of tons of machinery and ambition off the planet, on average every 35 hours. Somewhere every day and a half, a rocket engine ignited, a payload separated, and humanity extended its reach with a metronomic regularity that would have seemed like pure fantasy just 2 decades ago. SpaceX hurled Starship, the largest and most powerful rocket ever built, toward orbit not once, but multiple times. Each flight a violent ballet of data and ambition, pushing the boundaries of what private industry can dare. China landed its Chang'e 6 probe on the far side of the moon, that hidden face no human eyes had ever directly witnessed, and returned samples from that alien terrain. India parked its Aditya L1 spacecraft at a gravitational sweet spot between the Sun and Earth, joining an elite club of nations that can navigate the deep space currents. NASA stands on the verge of Artemis, ready to send human beings back to lunar soil for the first time in over half a century. The numbers don't lie, they shout. More payloads reached orbit last year than during the entire first decade of the space age combined. More nations now have their own ride to space than at any point in history, and the private money flowing into space ventures each year now dwarfs the government budgets that funded the original race to the moon. Scroll through the headlines and you'll find the narrative of inevitable expansion. Billionaires competing for cosmic bragging rights. Astronauts from multiple countries living and working overhead right now. Press releases confidently announcing lunar habitats, Mars colonies, orbital factories, and space tourism ventures taking reservations for flights promised in years, not decades. The language is saturated with the vocabulary of permanence. Sustainable exploration. Permanent presence. Long-duration habitation. The words weave a story that humanity is poised at the threshold, that the technical puzzles are largely solved, that only funding and willpower separate us from a future where humans live and work across the solar system. It's a compelling story, but it is a story built on a foundation of profound, deliberate, and dangerous omission. Here is what these dazzling numbers and declarations conceal. Every single one of these achievements, without exception, represents a demonstration. A proof of concept. A mission with a neat, clean arc. A beginning, a middle, and an end. Not one of them demonstrates what actually matters for a permanent human presence beyond Earth. This distinction between visiting and staying is the most important truth about our modern space age, and it is the truth almost nobody is talking about. Let's break down what a demonstration mission proves. A rocket launches. Controllers watch lines of telemetry as it punches through the atmosphere. Stages separate on cue. A spacecraft arrives at its intended parking spot, be it low Earth orbit, a lunar trajectory, or the interplanetary dark. Astronauts perform experiments, conduct spacewalks, maybe descend to another world's surface. Data streams home to eager scientists. The mission concludes. There are celebrations, press conferences, papers published, contracts renewed. Politicians claim victory. The media spotlight pivots to the next spectacular leap. This is the dance we have mastered. Now, hold that image in your mind and contrast it with what sustained operations actually require. Systems that function continuously for years, even decades, without replacement parts shipped from Earth. Life support that produces more oxygen and water than it consumes. Food production that can feed a crew indefinitely without a single resupply shipment. Manufacturing capabilities that can repair or rebuild critical equipment, using materials dug or harvested locally, not launched at a cost of tens of thousands per kilogram. Power systems that operate through gradual degradation without a team in Houston intervening. Crew rotation systems that don't depend on launch windows measured in years. None of this exists. Not in low Earth orbit, not on the Moon, not on Mars, not even in the slide decks and CG simulations that promise it. The chasm between these two states, between the demonstration and the sustained presence, is not a gap. It is a yawning abyss. And we are collectively pretending it's a small step. Consider our crown jewel, our most audacious proof that humans can live in space. The International Space Station. It orbits about 250 miles overhead. On a clear night, if you time it right, you can see it, a bright, fast-moving pinprick of light, completing a full lap around our planet every 90 minutes. It represents humanity's only example of continuous human presence in space. Astronauts have lived aboard it without interruption since November of 2000. Nearly a quarter-century of continuous occupation, generation after generation of crews launching, working, returning, thousands of scientific experiments, spacewalks to maintain and upgrade its exterior, an unparalleled feat of international cooperation. Surely this proves we can sustain ourselves off-world? It proves the exact opposite. The ISS is the ultimate monument to our Earth dependence. It consumes approximately 6 tons of supplies from Earth every single month. Not occasionally, not during emergencies. Every month, without fail, cargo spacecraft launch from Florida, Kazakhstan, Japan and Virginia, hauling food, water, spare parts, experiments, clothing, and every other necessity the station cannot produce for itself. Every calorie consumed by every astronaut was grown on a farm, processed in a factory, packaged, and shipped across multiple terrestrial transportation networks before being violently hurled into orbit. Every byte represents mass that made the journey from Earth's soil to an outpost that cannot grow a single head of lettuce at a meaningful scale. Their water is recycled at about 90% efficiency, a fact that sounds impressive until you do the math. 10% of all water used, for drinking, cooking, hygiene, experiments, is lost forever and must be constantly replaced from terrestrial sources. The station's air leaks, slowly but incessantly, requiring regular top-ups of nitrogen and oxygen from tanks launched from Earth. Every component that wears out, every pump that fails, every circuit board that fries must be replaced with a part manufactured, tested, and launched from our home planet at staggering cost. Without this constant, unwavering resupply, the ISS would become uninhabitable in about 3 months. Not from a dramatic explosion, but from the quiet, inevitable exhaustion of consumables. Carbon dioxide would accumulate, systems would degrade without replacement. The station is not a demonstration of sustainable space habitation. It is a demonstration of how much continuous effort Earth must expend, a perpetual logistical marathon, just to maintain a single small outpost in the easiest possible location, low Earth orbit. And that's the crucial, terrifying point. Low Earth orbit is the kindergarten of space habitation. It offers advantages that the Moon or Mars simply do not. A cargo vehicle launching from Florida can dock at the ISS in about 24 hours. An emergency can see a crew evacuated back to Earth's surface in hours using the Soyuz or Crew Dragon spacecraft permanently docked as lifeboats. Mission control can troubleshoot problems in real time, with mere seconds of communication delay. None of these safety nets exist for the destinations where we now claim we want to build permanent homes. The Moon is 250,000 miles away. Resupply takes days. Emergency evacuation requires hours of preparation. Mars is another universe of isolation. At its closest, it is 34 million miles distant. At its farthest, 250 million. Transit times are 6 to 9 months one way using current technology. Communication delays stretch to 20 minutes each way. Emergency evacuation is impossible once you've passed a certain point in the trajectory. A resupply mission would need to launch years in advance to arrive when needed. The question is brutally simple. If we cannot sustain a presence in our own backyard, in low Earth orbit, without Earth holding our hand every single month, how can we possibly hope to do it in places where that helping hand is suddenly orders of magnitude weaker, slower, and more expensive? The spectacle of the race makes us feel like we're charging forward, but the logistics whisper that we're still just visiting, and we've brought our entire home with us in little pieces, sent up month after month after month. This is the silent crisis. And to understand how deep it goes, we need to look past the rockets and the landings, and into the fragile web of life we take for granted here and cannot replicate out there. The Space Shuttle program stands as a devastatingly clear case study in this chasm between demonstration and sustainment. For 30 years, NASA operated the most sophisticated reusable spacecraft ever conceived. 5 orbiters flew 135 missions between 1981 and 2011. They built the International Space Station, module by module. They deployed and then heroically repaired the Hubble Space Telescope. They launched probes, satellites, and countless payloads. They carried more astronauts to orbit than any vehicle in history. The shuttle was supposed to make space access routine. Original projections dreamed of 50 flights a year. The reusable design was meant to slash costs compared to throwing away rockets each time. Regular flights would normalise human presence in orbit. Sustainable operations, the thinking went, would naturally emerge from this demonstrated capability. None of it happened. Each shuttle flight cost around $450 million in 1990 money. Adjusted for inflation, that's roughly $1.6 billion per mission. The promised cost reductions never materialised. The promised flight rate never approached the dream. The maximum reached was 9 missions in a single year, not 50. The reality of reusability was a brutal lesson in complexity. Refurbishing an orbiter between flights required months of intense labour by thousands of specialised technicians. The thermal protection system alone, those iconic heat-resistant tiles covering the spacecraft's belly, demanded the individual inspection of over 20,000 tiles after every single flight. Many needed replacement. Some missions required over 100 new tiles. The main engines required complete disassembly and inspection after each use. The solid rocket boosters splashed into the ocean had to be recovered, cleaned, refurbished, and restacked. The enormous external tank was expended and burned up every time, requiring a continuous manufacturing pipeline for new ones. The program ended in 2011, not simply because it failed spectacularly twice, claiming 14 lives in the Challenger and Columbia disasters, but because after 30 years and over 100 flights, the shuttle could never deliver the sustainable, routine access to space that justified its existence. 3 decades of demonstrated capability produced exactly 0 years of sustainable operations. The shuttle proved we could reach orbit repeatedly with a partially reusable vehicle. It demonstrated precisely nothing about sustainability. Each flight remained as dependent on a massive, expensive, earth-bound ground infrastructure as the one before it. When the program ended, nothing remained that could continue operating without it. It was a magnificent demonstration that ended, leaving no sustainable path forward. This legacy haunts every modern program. We mistake frequency for permanence, reusability for independence. The shuttle should have been our warning. This brings us to the core, unspoken assumption poisoning the modern space race. Every headline about Artemis, about Chinese lunar bases, about private space stations and Mars colonies operates under a single, fragile premise. The assumption that demonstration leads naturally to sustainment, that proving you can reach a destination proves you can stay there. This assumption has never been validated anywhere beyond Earth. In fact, our greatest triumph is the perfect proof of its falseness. The Apollo program reached the moon 6 times. Between 1969 and 1972, 12 human beings walked on lunar soil. They spent a combined 80 hours outside their landers, exploring terrain no life had ever witnessed. They collected hundreds of pounds of samples, deployed scientific instruments, drove electric rovers, and transformed our understanding of planetary science. By any measure, this was a stunningly successful demonstration of human lunar operational capability. If demonstration naturally led to sustained presence, we would have maintained a continuous lunar outpost for over 50 years by now. Yet Apollo produced no sustainable lunar presence whatsoever. The program ended abruptly after just 3 years of surface activity, not because of technical failure, but because the entire architecture was designed from the ground up, literally, around Earth-based logistics for every single aspect. The astronauts carried everything they needed from Earth. They produced nothing on the moon. They extracted no resources. They manufactured no equipment. They left behind descent stages and flags, but no infrastructure a follow-up mission could use, no supply caches, no habitable modules, no power grids, no communication relays. Each landing was a complete, self-contained expedition, not a building block toward permanence. Apollo 11 carried everything needed for Apollo 11. Apollo 12 carried everything for Apollo 12. No cumulative infrastructure progress occurred. When the political winds shifted after the 6th landing, there was nothing on the lunar surface. No functional asset, no economic hook, to justify continuing the staggering expense. The capability to reach the moon remained, locked in blueprints and in the minds of engineers. But that capability is a perishable commodity. Within years, production lines shut down, engineers dispersed, skills atrophied. The moon fell silent again. Not because getting there became impossible, but because no economic, scientific or political rationale could survive the brutal cost calculus of a logistics model wholly unchanged from the first mission. Apollo demonstrated we could reach the moon. It demonstrated absolutely nothing about whether we could stay, and the 53 years of silence since the last astronaut left have produced no meaningful progress on that fundamental question. We are now planning to return, promising it will be different this time. But are we actually building a path to stay, or just a more expensive, more complex way to visit? The current Artemis program promises to break the Apollo mold. NASA officials now use the vocabulary of lessons learned. They speak of sustainable lunar exploration. They describe the Gateway, a small station in lunar orbit intended to support surface operations across multiple missions. They reference plans for surface habitats, pressurized rovers, and systems to extract resources like water ice. They paint a vision of a budding lunar economy where commercial companies provide services and sell resources. It sounds transformative, like we finally understood the assignment. But examine the actual hardware, the actual timelines, and the sustainment question becomes deeply uncomfortable, even unnerving. Artemis relies on the Space Launch System rocket, a vehicle derived from space shuttle components that costs approximately $2 billion per flight and is almost entirely expendable. Its core stage, powered by 4 RS-25 engines from the shuttle, burns up in the atmosphere every time. Its solid rocket boosters splash into the Atlantic and are not recovered. Each SL's launch requires years of manufacturing and preparation across facilities in multiple states, involving thousands of workers. The current maximum production rate is optimistically 2 flights per year. This launch cadence cannot sustain a permanent lunar presence. It can barely sustain the handful of planned demonstration missions through the end of this decade. Then there's the Gateway. This orbital station, the supposed stepping stone for sustainability, will itself require constant resupply from Earth, exactly like the ISS. It offers no manufacturing capability, it produces no food, it generates no fuel, it extracts no resources. Every litre of water, every kilogram of food, every spare part it needs must be launched from Earth, transported across 3 days of spaceflight, and meticulously transferred aboard. The logistics chain stretches from factory floors in Alabama and California to a station orbiting the moon. Every single link in that chain depends on continued funding, continued political will, and an uninterrupted industrial base on Earth, all to support an outpost that produces no economic return. The lunar surface architecture faces identical dependency problems. NASA's chosen human landing system, SpaceX's Starship variant, operates on a cascade of assumptions that have never been demonstrated at operational scale. The plan assumes that multiple Starship tanker vehicles will successfully transfer hundreds of tons of cryogenic propellant in orbit. It assumes orbital depots can store this supercold fuel for long periods without excessive boil-off. It assumes a lunar Starship can be refueled repeatedly in orbit for multiple landing missions. SpaceX has never transferred propellant between 2 Starships in orbit. No orbital propellant depot of the required scale has ever existed. The largest fuel transfer ever attempted was a few hundred kilograms on the ISS, not the hundreds of tons needed for the moon. No Starship has ever landed on the moon, or any celestial body. These are not minor engineering details to be ironed out. They are fundamental, show-stopping operational capabilities that determine whether the entire architecture is viable. If propellant transfer fails to achieve the required efficiency, the architecture collapses. If depot storage loses fuel faster than predicted, mission timing becomes impossible. If landing accuracy isn't perfect, crews die. The entire audacious plan is a high-stakes demonstration pretending to be a sustainability blueprint. China's lunar ambitions mirror this pattern with their own distinct flavour of the sustainment gap. Their Chang program has demonstrated remarkable robotic capabilities, landers operating for extended periods, sample returns from both the moon's near and far sides. The far side landing was a genuine historic first, but their crude lunar timeline, targeting human landings around 2030 with eventual bases, assumes the same unsupported leap from demonstration to sustainment. Their architecture depends on the Long March 9 Super Heavy rocket, still on the drawing board. It requires new crew spacecraft, new landers, new surface systems, all following the demonstration model. Fly, test, learn, celebrate. But sustained presence requires more than working hardware. It requires closed loops, regenerating resources, self-maintaining systems, and an economic or scientific rationale durable enough to survive political transitions. China has demonstrated none of these requirements any more than America has. Both nations are racing to demonstrate the how of getting there, while entirely sidestepping the how of staying. The private sector offers no magical escape from this fundamental constraint. Companies like SpaceX have undeniably revolutionized launch through reusable rocket technology. Falcon 9 boosters land on drone ships and fly again weeks later. This is genuine, monumental progress toward making space access routine. Reusable rockets have increased launch frequency and slashed per kilogram costs, enabling projects like the Starlink mega constellation. But critically, reduced launch costs do not solve sustainment. They make demonstration cheaper. They enable more frequent missions. They lower the barrier to reaching space. They do absolutely nothing about staying there. A Falcon 9 launch costs about $67 million. A fully reusable Starship might one day cost $10 million or less per flight, though that remains speculative. These numbers suggest a dramatic improvement in access. Now run the math for sustainment. The IS needs 6 tons of supplies monthly. At current launch costs of $20,000/kg, that's $120 million monthly. $1, $4 billion annually, just for logistics to keep 6 people alive. Reduce launch costs to an optimistic $1,000/kg through reusability. Logistics still cost $6 million monthly, $72 million yearly for one small station. This excludes crew rotation, unexpected hardware failures, ground support and mission control. Reduce costs by another order of magnitude. It's still millions annually for one outpost. Now multiply that for multiple stations. Add lunar outposts. Contemplate Mars bases. The numbers explode faster than cost reductions can chase them. Sustainable space operations cannot depend on continuous resupply from Earth. Not because of launch costs alone, but because the entire model assumes Earth remains perpetually willing, able, and stable enough to sustain that supply chain indefinitely. What happens when budgets are cut in a recession? When a pandemic disrupts global manufacturing? When a war fractures international partnerships? When the specialized factory making a critical component burns down? These aren't hypotheticals. They are historical certainties. Current architectures have no answer for them. They assume the chain will never break. The IS faces decommissioning around 2030, with a transition to commercial stations operated by companies like Axiom Space. But those commercial stations depend on NASA as their primary customer. They depend on the same government funding, the same political will, the same fragile supply chains. If government priorities shift, the commercial model collapses. Ownership structures change, but the fundamental lethal dependencies do not. Every proposed commercial venture traces its lifeline back to Earth-based manufacturing and political stability. None have been stress-tested against sustained disruption. None describe how operations continue if the logistics chain is severed. This is the real problem, hiding in plain sight behind the glitter of reusable rockets and falling costs. The race generates excitement through the appearance of momentum, but that momentum is operationally fragile. Every achievement depends on supply chains stretching back to factories, farms, and facilities on Earth. Every crew depends on life support that depends on consumables that depend on resupply missions that depend on funding that depends on political will. Cut any link, and everything downstream fails. Not with a bang, but with a slow, inevitable suffocation. Systems degrade. Consumables run out. Crews must evacuate or die. No current architecture has an answer for this. No planned mission demonstrates the closed-loop systems that true sustainability requires. We are building a taller ladder to reach the same fragile perch. Part 4 of 15. To understand the sheer, overwhelming scale of this dependency, we must move past rockets and stations and look at the most basic human needs. Let's start with food. Every human being requires roughly 2,000 calories daily for basic metabolic function. Add the physical labour and psychological stress of spaceflight, and that climbs toward 3,000 or more. Astronauts on a spacewalk burn energy like marathon runners. Now consider satisfying that demand when the nearest grocery store is 250 miles straight down, accessible only by a spacecraft costing tens of millions of dollars. NASA's space food system provides about 1.7 kilograms of food per person per day. This food isn't normal. It must survive launch G-forces that would crush a bread loaf, endure extreme temperature swings, remain safe for consumption for years, and be prepared in microgravity where crumbs become hazardous and liquids float away. These requirements eliminate almost all fresh food. You cannot launch a salad. Lettuce wilts, tomatoes bruise, bread moulds. What remains is processed, industrial sustenance, freeze-dried meals you add water to, thermostabilized pouches like military rations, irradiated meats, compressed nutrition bars designed for caloric density, not pleasure. For a crew of 6, daily food mass approaches 10 kilograms including packaging. That's 300 kilograms monthly, 3,600 kilograms, nearly 4 metric tons annually just to prevent 6 people from starving. This calculation is for the food alone. It excludes the mass of preparation equipment, heaters, utensils, waste processing systems, refrigeration, and backup supplies. Extrapolate to larger crews and longer missions, and the logistics become monstrous. A permanent lunar outpost with 12 rotating residents would need over 7,000 kg of food annually, assuming perfect delivery with no spoilage or damage. A Mars mission is a food logistics nightmare. A 6-month transit for a crew of 6 needs nearly 4,000 kg of food. 18 months on the surface adds another 10,000 kg. The 6-month return adds 4,000 more. A single Mars expedition requires launching roughly 20,000 kilograms of food just to prevent starvation. At current launch costs of $9,000 to $20,000/kg to low Earth orbit, that's $400 million for food alone, per mission. Even with wildly optimistic cost reductions, it's still tens of millions, and this is just to get the food to Earth orbit. The tyranny of the rocket equation governs all space logistics with mathematical brutality. Every kilogram you want to deliver to a distant destination requires propellant to accelerate it. That propellant has mass, requiring more propellant. The tanks have mass, the engines have mass. It's an exponential relationship. Delivering 1 kg to the Martian surface may require launching 10 to 50 kg from Earth's surface, depending on the architecture. So that $400 million in food logistics might balloon to several $billion in total launch costs for the full propellant chain to get it to Mars. We are talking about spending upwards of $500 million just to feed 6 people for 3 years on a single mission, without establishing any capability for the next mission to cost less. This is not a pathway to permanence. It is a recipe for the most expensive camping trip in history, repeated at best once a decade. Water presents an even more critical and complex challenge. The human body needs about 2 litres of water daily under sedentary conditions. With exertion, it climbs toward 4. Hygiene, food preparation, and equipment cooling add more. Total water consumption on a spacecraft runs roughly 3-4 litres per person per day. For a crew of 6 over a year, that's approximately 8,000 litres, 8 metric tons of the most essential substance for life. Launching that annually would cost $60 million at current rates. Even at future reduced rates, it's tens of millions per year for a single outpost. This is why water recycling is non-negotiable for any extended flight. Current systems on the ISS are engineering marvels, recovering about 90% of water through humidity capture and urine processing. Astronauts drink recycled urine purified to standards exceeding most tap water on Earth. But 90% efficiency is not sustainability, it is slow consumption. 10% of all water used is lost every day. It evaporates into unreachable corners, remains bound in waste, or contaminates equipment. The losses accumulate relentlessly. A crew of 6 using 30 litres daily at 90% recycling loses 3 litres every single day. Over a year, that's nearly 1,100 litres lost. Over a 3-year Mars mission, cumulative losses exceed 3,000 litres, 3 metric tons of water that must be launched from Earth because the loop isn't closed. Improving efficiency from 90 to 95% sounds modest, but represents an extraordinary engineering hurdle. Each percentage point requires more sophisticated, more power-hungry, more maintenance-intensive equipment. The asymptote toward perfection demands exponentially increasing investment for linearly decreasing returns. And even 99% efficiency still means 1% losses, over 300 litres lost on a Mars mission that must come from somewhere else. For destinations with routine Earth resupply like the ISS, these losses are manageable. Cargo ships bring replacement water, but for the Moon or Mars, the mathematics become existential. The much-touted solution is local resources, specifically lunar water ice. Scientists have confirmed ice deposits in permanently shadowed craters at the lunar poles. This ice could, in theory, supply drinking water, oxygen through electrolysis, and hydrogen for fuel. The resource exists. The physics supports extraction. This vision powers countless mission architectures and justifies massive investments. But potential resources and operational extraction are separated by a chasm of engineering reality. No technology has ever extracted lunar ice at scales approaching human needs. No system has converted raw lunar ice into safe drinking water. No infrastructure exists to transport water from polar craters to equatorial habitats. The entire concept remains theoretical. Even if lab-scale extraction worked, operational deployment faces unprecedented challenges. Permanently shadowed craters are, by definition, in eternal darkness and cold, below 170 C, plunging to 230 C. The same shadows that preserve the ice block the sunlight needed to power extraction. Mining would require nuclear power never used on the Moon, or impossibly long power cables from sunlit crater rims. At those temperatures, lubricants freeze, metals turn brittle, seals fail. Mining equipment would need its own heating systems to avoid destruction, requiring more power. The circular dependency is stark. Establishing lunar water extraction requires launching extraction equipment, processors, power systems, and transportation from Earth. That equipment must then function reliably for years without replacement parts from Earth, which is the whole point. But achieving that reliability requires extensive testing, which requires prototypes, which requires manufacturing, all tracing back to Earth. The independence promised by lunar resources requires decades of profound dependence to establish. This timeline extends far beyond political cycles, beyond institutional commitment, beyond the careers of the engineers who start the work. It is a paradox we have not begun to solve. Part 5 of 15. Atmospheric management adds another compounding layer of consumable dependency. Human metabolism consumes oxygen and produces carbon dioxide. 6 people produce about 1 kg of CO daily. This gas must be scrubbed from the cabin air and replaced with oxygen. The margin between habitability and catastrophe is terrifyingly thin. CO concentrations above 1% impair cognition, above 5%, unconsciousness follows within minutes, above 10%, it's fatal. Current systems use either consumable absorbents like lithium hydroxide canisters, which chaturate and must be replaced, or regenerative molecular sieve beds that capture and release CO when heated. The Apollo 13 crisis famously revolved around improvised CO scrubbers when an explosion crippled their spacecraft, a dramatic illustration of this consumable dependency. Modern systems are primarily regenerative, but regeneration is never perfect. Sieve beds accumulate contaminants and lose efficiency. Seals degrade. Sensors drift. Every component needs periodic maintenance, replacement, or recalibration. Beyond CO, spacecraft atmospheres accumulate trace contaminants, chemicals off-gassed from plastics, electronics, insulation, and crew metabolism. Some are merely unpleasant odours, others are toxic over time. Activated charcoal filters and catalytic oxidizers handle these, but they too require periodic replacement, power, and maintenance. Oxygen itself must come from somewhere, either stored reserves or electrolysis of water. Electrolysis splits water into breathable oxygen and waste hydrogen, which is typically vented, representing another resource loss. Every breath an astronaut takes is a carefully rationed commodity, tracked and managed, ultimately dependent on a supply chain originating on Earth. Power systems anchor all these consumable loops in another fundamental physical dependency. Life support, water recycling, food storage, communications, everything that keeps a crew alive requires continuous, reliable electricity. For most spacecraft, this comes from solar photovoltaic arrays. They work well in the vacuum of space, free of weather and atmosphere. But they degrade. High-energy space radiation damages the semiconductor crystals. Micrometeorites create pinholes. Thermal cycling from sunlight to shadow stresses connections. After 20 years, arrays may produce only 70–80% of their original power. These arrays have been replaced and upgraded multiple times. Without that maintenance, power would have dropped below usable levels years ago. Batteries store energy for shadow periods, but they too degrade with each charge-discharge cycle, eventually requiring replacement, more mass launched from Earth. For destinations beyond Earth orbit, solar power's limitations become severe. The Moon has a 14 Earth day-night. Storing enough battery power for 2 weeks of darkness is a colossal, undemonstrated challenge. Mars receives less than half the solar intensity of Earth orbit, and global dust storms can blot out the Sun for months, as the rover Opportunity learned when its solar panels were coated beyond recovery. The alternative is nuclear power. Small fission reactors could provide steady, location-independent power. Projects like NASA's Killer Power have demonstrated small-scale reactor technology, but no nuclear reactor has ever operated on the Moon or Mars. Radiation shielding adds massive weight. Public and political acceptance of launching nuclear material is a huge hurdle. Maintenance requirements for nuclear systems in space are a complete unknown. Every power solution eventually fails. Every one requires maintenance and spare parts. Every spare part must be predicted, manufactured, tested, and launched from Earth at a cost that accumulates relentlessly. This interconnected web of dependencies, food, water, air, power, creates a fragility that pervades every aspect of space operations. It means a single failure can cascade. Consider a pump failing in a water recycler on a Mars outpost 8 months from the next Earth resupply. The crew can't wait for a replacement. They must repair it using only what's on hand. This demands extensive inventories of predicted spare parts, launched years in advance at enormous cost. But which of the 10,000 possible components will fail? Mission planners face impossible trade-offs. Every kilogram devoted to spares is a kilogram not spent on food, water, or science. Repair also demands crew expertise across every critical system: electrical, mechanical, chemical, computational. Training such universally skilled astronauts takes years. And improvisation, like the Apollo 13 fix, becomes a desperate gamble. That miracle worked because communication delays were seconds, the mission lasted days, and the available materials were compatible. On a Mars mission, communication delays are minutes. The mission lasts years, and you can't know if you have the right stuff to jury-rig a solution. The margin for error vanishes. This is the sustainment problem in microcosm, not just having the technology, but having the robust, redundant, and locally maintainable systems to survive the unpredictable in an environment where rescue is impossible. We have none of it. Part 6 of 15. Human constraints compound these logistical nightmares into seemingly insurmountable barriers. Start with the people themselves. Over 12,000 applied for NASA's most recent astronaut class. From these elite pilots, scientists and engineers, 10 were selected, an acceptance rate of 0.083%. This selectivity isn't vanity, it reflects the extraordinary physical and mental demands of space. After selection, candidates face 2 years of basic training, mastering multiple spacecraft systems, learning to troubleshoot fatal failures under time pressure, practicing spacewalks in bulky suits that fight every movement, becoming proficient across scientific disciplines from biology to geology. They train for emergencies unique to space, fire in microgravity, rapid decompression, medical crises with no hospital nearby. Their physical conditioning rivals that of professional athletes, preparing bodies for the shock of launch, the fluid shifts of weightlessness, the deconditioning of long missions. After basic training, mission-specific preparation adds another 2 to 3 years, especially for IS expeditions, involving countless hours in simulators and mock-ups. This pipeline produces astronauts capable of surviving in low Earth orbit. It does not produce astronauts prepared for the challenges of sustainable deep space presence. Now consider the scale required. Keeping the IS continuously occupied with 6 crew requires a steady rotation. With 6-month missions, you need at least 12 trained astronauts cycling through annually. In reality, you need backups for every crew, and a pipeline to replace retirees. The steady-state requirement is 25-30 active astronauts ready to support just 6 people in space at any time. NASA's active core is about 42. They must cover IS operations, commercial crew missions, Artemis training, and public duties. The entire global pool of active, trained astronauts and cosmonauts is only about 120 individuals. 120 people to support all current space activities and the alleged imminent expansion to the Moon and Mars. This constraint becomes crippling for expanded operations. Artemis lunar missions require completely different training from IS expeditions, new spacecraft Orion, Starship Hills, new lunar geology skills, new surface operation procedures. Training astronauts for the Moon, while maintaining its rotations, would strain current infrastructure beyond capacity. Sustainable lunar presence, with crews rotating through Gateway and a surface base, would require training dozens of lunar-qualified astronauts at a rate exceeding total current global graduation rates. Mars missions amplify this beyond any precedent. Transit times of 6-9 months each way mean crews are committed to 2.5-3-year missions. No human has ever experienced a spaceflight that long. Training for such a mission might take 5 years of dedicated preparation, learning systems that have never flown, practicing for environments no human has experienced. An astronaut launching to Mars in 2038 would need to be selected by 2032 to allow for basic training and 5 years of mission-specific prep. The selection pool for that astronaut would need to be identified by 2030. Current selection and training rates cannot produce Mars crews at any meaningful cadence. Training 1 crew per decade might be possible with heroic effort. Training crews often enough for a rotating presence would require an institutional transformation no nation has begun. It would mean building more facilities, more simulators, hiring more instructors, who are often experienced astronauts pulled from flight status, all requiring investments years before paying off. The lag between decision and capability spans political cycles that reliably reset priorities. But training is just one human limit. Radiation exposure creates a biological barrier no amount of training or funding can overcome. Earth's magnetic field shields us from the relentless bombardment of galactic cosmic rays, heavy atomic nuclei accelerated to near light speed, and from solar particle events, violent bursts from the sun. Beyond this magnetic shield, the radiation environment is alien and lethal to human biology. NASA sets career radiation limits to prevent excessive cancer risk, about 1,000 millisieverts. For context, the average Earthling gets 3 MSV per year from background radiation. IS astronauts, still partially protected, get about 150 MSV on a 6-month mission. Beyond low Earth orbit, exposure skyrockets. On the lunar surface, crews might accumulate 180 MSV in 6 months. On a Mars mission, estimates suggest 300 plus MSV for the round-trip transit alone, plus several hundred more during surface stay. A single Mars mission could consume half an astronaut's career limit. This creates an insane operational constraint. Mars astronauts could never become experienced Mars astronauts. The individuals who learn the most about surviving on Mars would be prohibited by their own accumulated radiation dose from returning to teach others. Institutional knowledge would transfer only through debriefs and documents, not the invaluable mentorship of experience. Contrast this with Antarctic exploration or submarine service, where veterans return repeatedly, building an irreplaceable body of practical wisdom. Mars denies us that. Shielding is partial and prohibitively heavy. Active magnetic shielding is theoretical. Pharmaceutical countermeasures are speculative and decades from approval. Radiation is a biological hard stop that defines the boundary of human deep space operations. It doesn't just limit careers, it prevents the very accumulation of experiential expertise that sustainable presence requires. Part 7 of 15. Psychological constraints add another dense layer of risk. Isolation and confinement alter the human mind in ways that 6-month stays cannot fully reveal. Analog environments, Antarctic winterovers, submarine deployments show increased rates of depression, anxiety, sleep disorders, cognitive decline, and intense interpersonal conflict. But these analogues are less extreme than a Mars mission. Antarctic personnel can go outside, see natural light in summer, and know evacuation is theoretically possible. Submariners can surface, communicate with family, and know the deployment has an end date. A Mars crew would have none of these psychological safety valves. For 6-9 months in transit, they are locked in a volume smaller than a small apartment with the same handful of people, with no possibility of separation, no natural light cycles, no real-time conversation with loved ones due to communication delays, and, most profoundly, no possibility of rescue or early return. Once on a Mars trajectory, you are committed. The psychological weight of that genuine, irreversible isolation, watching Earth shrink to a pale star, is a burden no human has ever borne for such durations. The overview effect, the profound perspective shiftess astronauts report from seeing Earth, would fade as home disappears into the black, replaced by the emptiness of deep space. Screening can select for resilience, but cannot guarantee stability over 3 years. History is littered with psychological breakdowns among carefully selected polar explorers and submariners. The probability of significant psychological issues on a multi-year Mars mission approaches certainty. The only questions are who breaks, how badly, and what the consequences are for crew survival. Medical constraints are equally daunting. Human bodies fail unpredictably. Appendicitis, kidney stones, dental emergencies, trauma from accidents, conditions easily treated on Earth become potential death sentences when the nearest hospital is months or years away. The ISS has a permanent lifeboat for medical evacuation. Mars does not. Crews would have to treat everything with the limited equipment and expertise on board. Surgical capability in microgravity or partial gravity is essentially untested. No major surgery has ever been performed in space. Blood behaves differently. Anesthetic protocols may not translate. Medications degrade over time, and radiation may accelerate this. A crew arriving at Mars after 9 months might find their antibiotics have lost potency. Sustainable presence would require addressing these psychological and medical limits through crew rotation. But rotating crews every 18-24 months to prevent psychological deterioration means constantly launching new 6-9 month transits, multiplying the logistics and radiation exposure problems across a larger population. None of this is solved. It is barely addressed in current mission architectures, which assume either that medical events won't happen or that crews will somehow cope. Maintenance expertise is another underappreciated human bottleneck. Everything in space eventually breaks. The ISS has experienced thousands of failures, most resolved by ground controllers in real time, or through procedures developed over weeks by Earth-based experts. For Mars, communication delays of up to 24 minutes each way turn real-time collaboration into asynchronous email. Crews must independently diagnose, troubleshoot, and repair complex systems with only the tools and spares on hand. A crew of 6 cannot include a specialist for every system. Electrical, mechanical, life support, propulsion, comms, medical. They must be generalists, yet the complexity of a spacecraft exceeds what any small group can master. The solution of relying on ground expertise evaporates. In situ repair through 3D printing is often touted as a solution, and while 3D printers in space can make simple plastic or metal parts, they cannot manufacture the complex electronics, sensors, processors, or specialized components that make up life-critical systems. They cannot print their own feedstock. The vision of astronauts printing any replacement part is science fiction, not a near-term capability. So we face a trilemma. We cannot carry all possible spares too heavy, we cannot rely on Earth for quick replacements too far, and we cannot manufacture most of what we need locally. Technology doesn't exist. This maintenance cliff is a fundamental blocker for sustainability. Political timelines ruthlessly exacerbate all these human and technical constraints. Space programs live and die by electoral cycles of 4-6 years. Politicians want achievements during their terms. Budgets fluctuate with the economy and competing priorities. These short-term cycles clash violently with the decades-long timelines of human spaceflight. Training takes years, spacecraft development takes decades, building institutional memory takes generations. The result is a brutal pattern of start-stop-restart. Apollo was cancelled. The shuttle was terminated. The Constellation program, the previous return to the Moon, was abandoned. Each followed the same arc: initial enthusiasm and funding, early development, then shifting priorities, budget cuts, and cancellation before achieving sustainable operations. Artemis is already facing this reality, with funding uncertainties and schedule slips. Why would it be different? Nothing in our political or economic systems suggests it will be. The modern space race, for all its apparent momentum, is operationally fragile. It is a collection of demonstrations running on assumptions of continuous funding, stable supply chains, and technological breakthroughs arriving on schedule. It has no plan for the inevitable disruptions, recessions, pandemics, wars, political upheaval that have marked human history and will continue to do so. Sustainable presence must survive these terrestrial storms. Our current architectures assume they won't happen, or that we can weather them with stockpiles. It is the greatest gamble of all. The proposed saviour for this dependency crisis is in situ resource utilisation, the elegant idea of using local materials instead of hauling everything from Earth. Extract water from lunar ice. Process the Martian atmosphere into oxygen and methane propellant. Mine regolith for construction. In principle, it's the only logical path to sustainability. The physics are sound. Laboratory experiments show it's possible, but the gap between a lab proof of concept and an operational, life-supporting infrastructure on another world is a chasm wider than the void itself. Take lunar water ice, the most promising near-term resource. We know it's there, in shadowed polar craters. But knowing it exists is a world away from mining it. Those craters are in permanent darkness at temperatures below 170 C. Equipment not only has to operate in cryogenic cold that makes metals brittle and seals fail, but it also needs power. Solar power is useless in permanent shadow. That means nuclear reactors or running miles of power cable from sunlit rims. Neither has ever been done. The mining equipment itself would need heating to avoid freezing solid, consuming more power. Then you need to process the dirty, likely contaminated ice into pure water, store it without freezing or boiling off in vacuum, and transport it potentially hundreds of kilometres to a base. Every step requires reliable hardware that must function for years without maintenance from Earth, the very capability we lack. No nation has funded development of such systems at a meaningful scale. A tiny Pathfinder experiment producing grams per hour is a demonstration. It does not validate the tons per day industry needed to change the logistics equation. The timeline from demonstration to operational ISRU stretches decades, far beyond the political horizons of any Artemis mission. Artemis missions through the 2030s will be wholly supplied from Earth. ISRU or not. Mars ISRU faces similar grand-scaling challenges. The MOXIE experiment on the Perseverance rover is a brilliant feat. It produced oxygen from the Martian CO atmosphere, but it produced about 6 grams per hour. To make the 0 centials and 30 metric tons of oxygen needed for a Mars ascent vehicle propellant, MOXIE would need to run continuously for over 570 years. Scaling that up by a factor of hundreds of thousands introduces monstrous engineering hurdles, thermal management, power requirements, hundreds of kilowatts, dust filtration, and maintenance over years of continuous operation. Mission architectures that bet crew survival on ISRU for their return ticket are gambling with lives on technology that exists at the benchtop level. Backup plans to launch all the return propellant from Earth exist on paper but would be astronomically expensive, likely dooming the mission politically. ISRU is not a lie, but it is a decades-early promise being used to justify near-term missions that will remain utterly Earth-dependent. It is the sustainment solution invoked to avoid confronting the sustainment problem today. Meanwhile, the laws of physics guarantee that any infrastructure we build will decay. Radiation damages electronics. Thermal cycling fatigues materials. Micrometeorites cause erosive damage. Dust infiltrates and abrades. On the Moon, 300°C day-night temperature swings every 2 weeks. On Mars, dust storms can last months and coat everything. Nothing lasts forever, especially in alien environments. The IS, with constant maintenance, shows its age through air leaks, degraded batteries and failing components. A lunar or Mars base with far less maintenance capability would decay faster. The proposed answer is autonomous robots and AI to perform maintenance. But those robots themselves would need maintenance, adding complexity. We are pushing the problem down the road, not solving it. The economic reality delivers the final, sobering blow. No human spaceflight activity has ever been economically self-sustaining. Government programs are loss leaders for prestige and science. Private companies depend on government contracts or speculative future markets. The customers for commercial space stations are government agencies. The business case for lunar water mining or Mars colonization is a fantasy of distant futures. Sustainable presence requires an economic engine, and none exists. It requires political will sustained across decades, through recessions, wars, and changes in leadership. Our history shows we cannot do this. We start, we stop, we forget. When programs end, engineers disperse, specialized suppliers vanish, and tacit knowledge is lost. The next program starts from near zero, relearning old lessons at great cost. This is the cycle we are in. Artemis, for all its sustainable rhetoric, depends on funding not yet appropriated, technology not yet proven, and political will that is historically fickle. It is a demonstration program wearing the clothes of a settlement program. The modern space race has a dazzling surface but a hollow core. We are proving we can go back to the moon. We are not proving we can stay. The footprints we leave will be as ephemeral as Apollo's unless we confront, with brutal honesty, the fact that we have not solved the fundamental problem, cutting the umbilical cord to Earth. Until we do, the race is just a faster, shinier way to visit, plant a flag, and come home. The cosmos doesn't care about our flags. It only respects systems that can endure. This cycle of institutional forgetting may be the most expensive cost of all. When the Apollo program ended, the production lines for the Saturn V rocket, the most powerful machine ever flown, didn't just go idle. They were dismantled. The jigs, the tooling, the specialized fixtures were scrapped or lost. The engineers, welders, and technicians who held the intimate, hands-on knowledge of how to build such a beast dispersed into the aerospace industry, retired or passed away. The blueprints remained, but blueprints are not capability. They don't capture the thousands of micro-decisions, the tacit knowledge of why a certain weld procedure worked, or how to troubleshoot a finicky valve that never behaved quite as predicted on paper. This loss is not anecdotal. It is a recurring tax on every generation of spaceflight. The Space Shuttle's retirement triggered a similar diaspora. The expertise in maintaining and refurbishing the orbiter's complex systems, the delicate thermal protection tiles, the reusable main engines, atrophied without a mission to serve. When the Constellation program aimed to return to the Moon, it found itself having to relearn techniques for large rocket fabrication that had evaporated. Now Artemis and the Space Launch System face this ghost. The RS-25 engines powering SLs are refurbished shuttle engines. The workforce that originally built them is largely gone. Restarting production of even these known components has been a slow, costly endeavour, plagued by supply chain issues for parts that no longer have active manufacturers. This is the hidden fragility of our space ambitions. The supply chain isn't just physical parts, it is human knowledge, and it is perishable. A program gap of a decade can sever that chain irrevocably. For all our digital archives, we cannot download decades of experience. Sustainable presence would require institutional continuity across 30, 40, 50 years, a continuous thread of missions, funding, and workforce development that has never been achieved in the democratic world. The political and economic systems of the major spacefaring nations are fundamentally anti-continuity. They thrive on change, on new priorities, on reallocating resources. Spaceflight demands the opposite, relentless, unwavering focus on a goal decades away. This mismatch isn't a bug, it's a fundamental incompatibility. China's system, with its longer-term planning cycles, might seem better suited, but it too faces the economic reality of diminishing returns and competing priorities on Earth. No system has yet demonstrated the ability to sustain the political and economic commitment for the half-century minimum that true Earth-independent presence would require. We are trying to build a cathedral that takes 100 years to complete, using construction crews hired on 4-year contracts. The result is a foundation, maybe a wall. Before the project is abandoned, the crew scatters, and the weather erodes what was built. Let's drill deeper into the most seductive promise. The closed loop. The vision of a self-sustaining habitat where waste becomes food, where exhaled carbon dioxide becomes oxygen, where water is perfectly recycled, is the holy grail. It's called a closed ecological life support system, or bioregenerative life support. On paper, it's elegant. Plants use photosynthesis to convert CO2 and water into oxygen and food. Human waste fertilizes the plants. Water is transpired and condensed. It's a miniature Earth in a can. We've tried. The most famous experiment was Biosphere 2, a 3.14-acre sealed glass complex in the Arizona desert in the early 1990s. 8 people entered for a 2-year mission to prove a self-sustaining ecosystem could support human life. It failed, spectacularly and instructively. Oxygen levels plummeted as unexpected soil bacteria consumed it. Nitrous oxide levels rose, impairing cognitive function. Food production fell short, forcing secret food imports. Insect populations exploded, then crashed. The carefully balanced biomes spun out of control. The experiment proved that ecosystems of that complexity are fiendishly difficult to manage, prone to unpredictable cascades, and incredibly fragile. Subsequent, smaller-scale research has improved our understanding. We can grow lettuce on the IS, but growing enough calorie-dense crops, potatoes, to feed a crew requires significant volume, light, and power. The lighting alone, replacing sunlight, consumes enormous energy. The systems are vulnerable to disease, pollination failures, and equipment malfunctions. The most optimistic experts suggest that even advanced bioregenerative systems might achieve 80–90% closure in the foreseeable future. That sounds high until you remember the math of compounding losses. A 10% leakage in a closed system on Earth is manageable. You just bring in some extra food and water. A 10% leakage on Mars means you still need to launch 10% of all consumables from Earth forever, with all the associated launch costs and fragility. That is not sustainability, it is a marginally reduced dependency. And we are nowhere near achieving even that 90% closure in an integrated, reliable, crew life-dependent system. The machines to support this, the hydroponics, the atmospheric processors, the waste recyclers, are themselves complex, power-hungry, and prone to failure. So we face a paradox. To become independent of Earth's biosphere, we must recreate its most complex functions inside the most hostile environment imaginable, using technology far less robust and resilient than the system we're trying to leave. It is perhaps the ultimate engineering challenge, and it is nowhere on the critical path of Artemis or any national Mars mission plan. They plan to go long before this problem is solved, which means they plan to go and remain dependent. Manufacturing in space is the other pillar of the independence fantasy. The idea is compelling: mine lunar or Martian material, feed it into 3D printers, and produce everything from spare parts to entire habitats. This field, called in situ manufacturing, has made real progress in the lab. On the IS, we've 3D printed simple plastic tools. That's a wonderful demonstration for replacing a lost wrench or a custom clamp, but it is a child's step compared to what's needed. Let's deconstruct what manufacturing really means for sustainability. A failed pump on a Mars habitat isn't just a plastic shell. It contains precision machined metal impellers, wear-resistant ceramic seals, copper wire windings for its motor, silicon-based microchips for its control system, and plastic composites for its housing. Each of those materials requires a separate, complex supply chain. To manufacture that pump on Mars, you would need 1. The raw ores containing the necessary metals, ceramics, and silicon. 2. The mining equipment to extract those ores. 3. The refining and smelting facilities to process ore into pure metal and silicon. 4. The chemical plants to produce plastics and ceramics from local carbon, hydrogen, and other elements. 5. The precision machine tools, mills, grinder to shape the components to micron tolerances. 6. The clean rooms and photolithography facilities to fabricate microchips. 7. The assembly lines and testing facilities. 8. The power grid to run all of the above. You are essentially trying to replicate the entire industrial revolution of Earth, from mining to high-tech fabrication, on another planet with a skeleton crew starting from zero. It is an absurd proposition for any timeline less than centuries. 3D printing bypasses some of the shaping steps, but it does not magic raw regolith into a functioning microchip. It requires highly refined, processed feedstock, filaments of specific plastics or powders of specific metal alloys. You cannot just shovel Martian dirt into a printer and get a circuit board. You must first create the feedstock, which requires all the refining infrastructure. The claim that 3D printing will let us live off the land is a gross, almost deliberate misunderstanding of industrial complexity. It confuses the final step of shaping with the immense pyramid of industrial processes that must support it. For the foreseeable future, in situ manufacturing will be limited to simple, non-critical items from pre-supplied feedstock. It is a supplement, not a foundation. The foundation, the ability to make a replacement for any broken component from local dirt, remains in the realm of distant science fiction. Our plans for sustainability are therefore built on a technological mirage. We point to 3D printed wrenches and promise future printed habitats, skipping the million steps in between. It is this kind of magical thinking that allows programs to claim a path to permanence while designing missions that are, in their bones, temporary. So we arrive at the heart of the dilemma. The core reason the modern space race is a sprint on a treadmill. The finish line, true, Earth-independent sustainability, is not even visible on the track we've built. We have optimized brilliantly for the wrong metric. We measure success in launches per year, cost per kilogram to orbit, number of rovers on Mars, flags planted. These are metrics of reach. They say nothing about stay. To measure stay, you would need very different, far more sobering metrics. Percentage of food produced locally, closure rate of water and air loops, mean time between failures for critical systems without Earth intervention, years of infrastructure operation without resupply, the economic value, generated per unit of Earth-based subsidy. On these metrics, our score is 0. Always has been. The International Space Station scores 0. Every lunar mission ever planned scores 0. Every Mars architecture on a drawing board scores 0. We have not begun the real work of sustainability because it is astronomically harder, more expensive, and offers no short-term political payoff. It is the work of generations. Instead, we've created a compelling illusion of progress. Reusable rockets are a genuine triumph, but they make the logistics of dependency slightly cheaper, not obsolete. Discovering water ice on the moon is a genuine breakthrough, but it is a potential resource, not a working utility. Landing bigger payloads is an engineering feat, but it just means we can ship larger care packages from home. The illusion is so powerful because each step feels like progress toward a frontier future. And in a narrow sense, it is. We are getting better at visiting, but visiting is not colonizing. Exploration is not settlement. We are confusing the two, and in doing so we are setting ourselves up for a colossal disappointment. The public, fed on a diet of Martian colony G and billionaire promises, expects a gradual, inevitable expansion. The reality will be a series of magnificent, isolated, breathtakingly expensive expeditions that end, each time with the crew coming home and the outpost falling silent, waiting for the next infusion of Earth's treasure to briefly reanimate. This is the Apollo pattern on steroids. It is not a path to becoming multiplanetary. It is a path to becoming very good at mounting planetary-scale camping trips. The real work, the slow, unglamorous, century-long project of building closed-loop biological systems, proving autonomous maintenance, and creating genuine economic activity in space, has not started. It is not funded. It is not the goal of Artemis, or of China's lunar base program, or of SpaceX's Mars ambitions. Their goals are to get there and to demonstrate the possibility of staying. But as we've seen, demonstrating the possibility is not the same as making it real. The former is a mission. The latter is a civilization-scale project. Consider the psychological and societal dimension of this. The original Apollo era was fueled by the existential, bipolar competition of the Cold War. The goal was clear, singular, and short-term: beat the other side to the moon. Once that was achieved, the driving force evaporated. The modern space race lacks such a clear, overwhelming geopolitical imperative. It is driven by a mixture of national prestige, scientific curiosity, commercial speculation, and the personal ambitions of billionaires. These are weaker, more diffuse motivators. They can sustain a series of projects, but can they sustain a century-long commitment to solving the grindingly hard problems of sustainability? When the first crew returns from Mars after a 3-year near-death experience of constant system failures, radiation, sickness, and psychological strain, what will be the public and political appetite to immediately fund the next, even more expensive mission? History suggests it will fade. The applause will be thunderous, then the bills will come due, and the question will be asked, what for? If the answer is merely to do it again, but slightly longer, the funding will dry up. Sustainability requires a reason to sustain beyond mere existence. On Earth, civilizations sustained themselves because they were born there, they had no choice. To sustain ourselves elsewhere, we need a compelling economic or survival imperative. A threat to Earth might provide it, but that's a grim motivator. Valuable resources might provide it, but no resource in space is currently valuable enough to justify the cost of extraction and return, save for scientific knowledge. The economic engine for space is missing. Until it is found, all presence will be a cost centre, a subsidy, a drain on terrestrial resources. And subsidies are the first things cut in hard times. This is why the cyclical pattern is almost a law of physics for publicly funded spaceflight. The dream of space settlement is ultimately a dream of post-scarcity, where the energy and material resources of the solar system are harnessed. But to get to that post-scarcity, you must first pass through a long valley of extreme scarcity, where every gram of water and watt of power is precious, and where the investment needed to climb out must come from a planet that has its own pressing problems. It is the ultimate bootstrap problem, and we are not being honest about how tall those boots are, or how weak the straps. Is there a way out? A path that isn't a cynical cycle of demonstrations? Perhaps, but it looks nothing like the race we see today. It would require a fundamental reorientation of goals, on a global scale. First, it would mean declaring a moratorium on the rush to plant flags, and instead focusing, collectively, on solving the fundamental closure problems in the easiest possible environment. Low Earth orbit. Imagine an international project, not to build another station, but to build a sustainability testbed. A facility dedicated solely to achieving and then exceeding 99.9% closure in air, water, and food loops. Its only mission to not need supplies, to fail, learn, and try again for as long as it takes. The goal would not be a crude mission to somewhere else, but the creation of a proven, reliable, closed-loop life support technology suite. This is the boring, essential plumbing of a spacefaring civilization. It is the equivalent of developing the steam engine before the age of railways. Second, it would require a similar dedicated, decades-long project in autonomous robotics and maintenance, not as a side project for a Mars mission, but as the primary goal. Sending robots to the moon for 10 years with the sole task of building, maintaining, and repairing a small infrastructure without humans present. Learning what fails, how to fix it, and how to design for robotic maintainability from the start. Third, it would require an honest economic assessment. Instead of promising grand lunar economies, we should target specific near-term space industries that can turn a profit without human presence, like certain forms of manufacturing that benefit from microgravity or vacuum. Use those profits to slowly fund further infrastructure, creating a genuine economic engine, however small. This path is slow. It is undramatic. It doesn't produce heroic astronaut stories or stunning landing videos on a regular basis. It is the work of engineers, biologists, and roboticists, not explorers. But it is the only path that builds capability cumulatively, brick by brick, toward true independence. It accepts that becoming a spacefaring species is not an adventure. It is an infrastructure project. And infrastructure projects are slow, costly, and unglamorous until they are complete and they change the world. The current race is the opposite. It is all adventure, all drama, with infrastructure as an afterthought. It promises a shortcut to the stars, but is building a road that loops back to Earth. We are chasing the glory of arrival while ignoring the grind of residence. The cosmos is patient. It has existed for 13.8 billion years. Our planet for 4.5 billion. Human civilization for a mere speck of that time. The idea that we are on the inevitable, imminent cusp of spreading life beyond our cradle is a beautiful, powerful, profoundly human story. But it may also be a story we tell ourselves to feel larger, more significant, more in control of our destiny. The universe is under no obligation to make that story come true. The reality is colder, harder, and governed by physics, biology, and economics that do not care about our dreams. The modern space race, for all its thunder and brilliance, has so far only proven that we can extend our reach. It has not proven we can loosen our grasp on home. Every astronaut, Every rover, every piece of hardware beyond our atmosphere is an avatar of Earth, utterly dependent on the planet it left. This is not a failure, it is the current state of our capability. The problem arises when we mistake this state for a transitional phase, when in fact it is the defining characteristic of our entire space endeavour to date. The crisis nobody talks about is that we have no proven roadmap to change that characteristic. We have hopes, dreams, and demonstration plans. We do not have a sustainability plan. Until we do, the race is a spectacle, not a migration. The footprints on the moon will remain silent testaments to what we can do when we focus all our might on a single, temporary goal. The orbiting stations will remain fragile bubbles of Earth life, sustained by a constant umbilical flow, and Mars will remain a distant, red temptation, always just one more technological breakthrough away. A breakthrough that never seems to arrive because it is not a single invention, but a million interlocking solutions to a million interlocking problems. This is not an argument for despair, nor for ending exploration. Exploration is invaluable. The science, the inspiration, the sheer human achievement of reaching into the void are worthy in themselves. But let us call it what it is. Exploration. Let us not dress it in the clothes of settlement and pretend the hard part is over once we land. The hard part begins when we try to stay. And on that front, we have not even begun the real work. The question for our generation is not, can we go back to the moon? We can, and we will. The real question is, will we choose to start the centuries-long, collaborative, unglamorous work of learning how to live there? That question hangs in the air unanswered, while the rockets fire and the headlines blaze and the race runs on faster and faster toward a finish line that doesn't yet exist. The universe watches, silent and indifferent, waiting to see if we are a species that can learn the difference between visiting a place and making it a home.